visualize what kind of information will be needed to get that solution, type of solution, and what is the given information in a problem. Just read through the problem. Even though this looks very simple problem, but this is very common and very useful day-to-day life example. Okay, it's very simple. The water is coming, so this is pipe. This is pipe. Water is coming through pipe, and say pipe is given a heat flux. Say it is coated with some jacket. It coated with jacket, and a constant heat flux is given through the pipe. So certainly what will happen? A temperature of water will increase. Okay, temperature of water will increase. Now we need to develop the temperature profile for this water. How temperature will change in a different direction, temperature profile. That is the problem. So consider a fluid flowing through water. So fluid is flowing through water with a constant density rho and thermal conductivity K. This is the thermal conductivity of water. This water is flowing through, and pipe density is of water, viscosity is of water. Okay, it is flowing through the pipe, hollow pipe. So and the heat capacity per unit mass at constant pressure, Cp. So heat capacity per unit mass, specific heat capacity, you can call it as a specific heat capacity. So that is Cp bar. The flow of the fluid, okay, flow of the fluid is assumed to be a laminar in a pipe. The fluid flow is laminar, it is given. Now certainly, because this is flowing fluid and it is heating up, so this is simultaneous heat as well as momentum transfer. Fluid is also flowing. It is also flowing. So to get the velocity profile, you need to work on a shell balance for momentum transfer. And then to get the heat profile, temperature profile, you need to work on a shell balance for heat transfer. So simultaneously heat and momentum transfer. So to simplify the problem, it is given that the flow is laminar. Flow is laminar and flow through pipe for laminar flow. Already we have developed the velocity profile. We have developed the velocity profile, flow of fluid through laminar, flow of fluid through a pipe, laminar flow, that already developed with a radius r. Initial temperature of the fluid is T1. So initial temperature of the fluid is P1. There is a constant radial heat flux. So the pipe is heated throughout the length L. So pipe is heated throughout the length L with a constant heat flux. Constant heat flux is given to pipe. Either it is coated with some resistive heating or some jacketed heating or anything you can think of, given wall pipe using electrical heating. Develop the equation for temperature profile and give the value of Nusselt number for this case. So this is very important actually. Many a times in interview also, this question will ask Nusselt number for laminar flow heated pipe with constant heat flux. What will be the value? So you will get a particular value. That we'll see how you are getting. That depends upon actually temperature profile, average temperature, and everything. So that Nusselt number also will develop in this class. So now based on this information, so first of all you should think what kind of solution you will be getting. So anybody in a class can voluntarily come up and discuss the important information given in a problem and what kind of solution you are expecting. Anybody in a class? Nobody in a class? Anybody in a class can come up and discuss. Nobody in a, who is having highest CGPA? Roll number 88.
Yes, sir.
Roll number 88 is there in a class?
Yes, sir.
Yeah. Yes. Who is having highest CGPA? Okay, tell me anybody who is among top 5.
There are many Kaushik, Abhini.
Yeah, roll number?
Roll number 35, 23.
Number 35. So we'll start with roll number 35. Yeah, roll number 35, Pranit.
Hello.
Tell me, Pranit.
Yes, sir. So since heat flux is given across the radius, so we can assume that maximum temperature will be at edges
Okay,
border.
very good. Maximum temperature will be at the wall.
Yes, sir. Wall. Yeah.
Minimum will be at the center. And this is
Center. Yes, sir.
symmetric actually. This heat
Yes, sir.
wall
So
is
we
heated.
can
Here
assume
also,
parabolic.
yeah, it will be parabolic. Temperature profile will be parabolic. Very good.
Yes, sir.
And whether temperature will change, what are the three direction? R, theta, and Z.
Yes, sir.
Variation of temperature in R direction, variation of temperature in Z direction, variation of temperature in theta direction.
So like theta symmetry, so no change.
Very good, very good. Excellent.
Constant heat flux across the tube. So Z direction also it won't change. It will change only in
Z direction it will not change.
Like across the whole wall, it's constant heat flux.
Yeah, it's constant. Say if length is 1 meter.
Yes, sir.
If length is 1 meter, so you have moved down a length 1 meter and you have moved down a length 2 meter. So certainly heat added will be more. Na?
Yes, sir. So it will increase.
It will increase in Z direction also.
Direction. Yes, sir. Yeah.
Temperature is a function of Z also. Whether temperature is function of R?
Yes, sir. Yeah. It's a maximum at a wall and minimum at a center.
Now this is very basic information you got. Now roll number 23. 23, Kaushik.
Yes, sir.
Kaushik. So what do you expect? Because there are two major modes of heat transfer, convection and conduction. Do you think that there will be variation in temperature in Z direction and variation temperature will vary in R direction? Are you convinced, Kaushik?
Yes, sir. It will vary.
Okay. So now tell me in R direction whether it will be convection or conduction. In R direction. Now there will be flow of heat in R direction because temperature is varying. So whether it will be dominated by conduction or convection in R direction.
Sir, by conduction only, sir, in R
Very
direction.
good. Very good. If temperature is varying and dominated by conduction, whether you are expecting a first order differential equation or second order differential equation with respect to R.
First order. First order.
Conduction.
Sir, second order conduction.
How, Kaushik? Because we have solved so many problems in conduction actually. Conduction in R direction, we have solved so many problems. So first of all, one differential equation will come from shell balance. Shell balance will also give one differential equation and another differential equation will come from a Fourier law of heat conduction. So it will be a differential of differential. So it will be a second order with respect to R. And how about Z? In Z direction, heat will be transported dominated by conduction or convection.
In Z direction, it will dominate by convection in Z direction.
So if it is dominated by convection, then it will be a first order differential equation or second order differential equation?
First order. Sir.
First order. So now
yes.
look, still now we have not solved any problem, but all the information is available with you. Okay, all the information, this is all the input which we will be discussing in the transport phenomena class from last 35 classes. So you are expected to get a second order temperature equation, temperature profile equation with respect to R, second order, and a first order with respect to Z. First order with respect to Z. This is what expectation. Maybe it will be different. Now, exactly similar problem we have solved. When we have multi-dimensional, now variable is temperature only. Variable will be temperature only. We will be discussing temperature profile only. Temperature, say, two-dimensional differential equation. Two-dimensional differential equation. One will be r-dimensional, another will be a z-dimensional. So this is single variable multi-dimensional differential equation. How to solve this problem? Anybody else in a class? Who is next? Kaushik? Next to you? Kaushik? Oh, roll number 24. 24, Bandi?
Hello, sir.
So how to solve this problem? When we have single variable multi-dimensional differential equation.
Shell balance.
Shell balance, okay, shell balance, whether you will be able to solve, first of all, it is second order with respect to R and first order with respect to Z. Expected will be a second order with respect to R and first order with respect to Z. Whether you have all mathematical weapons available with you to solve this problem, or what kind of method you needing to solve this problem? Whether we have encountered any problem similar to this, Bandi?
Equation of
Who is there with you? Yeah, Bandi?
hello.
Who is there with you?
No one, sir.
So what
It's
kind of
coming resound, I think.
Okay.
Sorry.
So actually we have solved this problem, and that problem was when there was a creeping flow around the sphere, and that velocity was a function. Velocity was varying in theta direction and phi r direction, theta and r direction, or phi and r direction. How we have solved the problem? So that this is one of the mathematical methods. So you can have an alternate method also. We need to expect the solution first of all. Expected solution. We'll start with the expected solution and then try to prove that this is the one of the possible solution. This is also one of the mathematical tricks, you can say, mathematical tricks. You can expect the solution and then try to prove that this is my solution. Okay, so this is what the method we are going to follow here. So this is expected temperature profile. So what will be expected temperature profile? As this is told, okay. So initially temperature is T1. Initially whole fluid is at say 25 degrees Celsius. This is the inlet of the pipe. The fluid is at 25 degrees Celsius, and then slowly as it enters, it will get heated up because a constant heat flux is given, and this is radius. Okay, this will be axis of the pipe actually. By the way, this is axis of the pipe. This is the pipe, and this is axis of the pipe. This point is axis, and this is the radius of the pipe. I am just highlighting half of this pipe, and this is the enlarged version. So slowly, what will happen? Highest temperature will be at the wall, and it will penetrate towards the center. Okay, and slowly, what will happen? It will have some parabolic. This is half parabola because this is the axis of the cylinder and this is the wall of the cylinder. So here temperature will be minimum, here temperature will be maximum. Okay, here temperature, and there will be some variation of temperature, parabolic variation of temperature from the center of the pipe to the wall of the pipe. So, but after some time, what will happen? This maximum temperature is attained. Maximum temperature is attained at the center. This profile is set. This profile is set. Whatever be the heat transported through this wall, each reach the center. Now thereafter, what will happen? The temperature start increasing. This is say baseline temperature T1. The temperature start increasing. So here this is say T2, and this is T3. T2 is greater than T1 and T3 is greater than T2. Slowly, likewise, there will be increase in temperature, but profile remains same. Okay, temperature profile remains same, but there will be increase in temperature as I move in a Z direction. So this will be so say at the end you will get some temperature T4 at the wall, at the center T4 and increasing, and this will be say final temperature that depends upon a length of the pipe. If length of the pipe is larger, this T4, this temperature will be larger, this temperature will be larger, this whole temperature will be larger, average temperature will be larger for larger length. Say length is 100 meter, say maybe sometime say length is 1 centimeter, maybe this profile is not set, so this will be the profile you will be getting 100 meter. Okay, 1 centimeter or so. Say after 100 meter you will be getting this temperature profile, after 200 meter you will be getting this temperature profile, after 500 meter you will be getting this temperature profile, and as you go on increasing the length of the tube, so average temperature, this minimum maximum temperature keep on increasing with the length of the tube. So what kind of solution, expected temperature profile? Roll number 39, Vedant. Vedant?
Yes, sir.
Yeah, what kind of expected temperature profile equation you can give so that it will fit all this temperature profile?
Yes, sir. So, sir, we see that with Z, the profile is changing after some time. It's just moving upward. So we can assume that it will be like linear with respect to Z. So maybe something like CZ
Very
and
good. Very good.
radius with radius, sir. It will be parabolic. So it will be some function of radius. So some f of r.
Excellent. 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 So this is what he is saying actually. T is a function of R and Z. So it is a linear with respect to Z. As you can see, it is linearly increasing with respect to Z. After some profile is set, So that initial you can neglect, but after some profile is set, it will be linear with respect to Z plus some function of R. That can be anything, as expected is a parabolic profile, temperature profile, but because there is a convection in Z direction also, which is dominating in heat transfer, it can be anything. Okay, this is what temperature profile you can expect. Now, as I told, I'm expecting, so it will be a second order differential equation with respect to R and first order differential equation with respect to Z. So how many boundary conditions are needed to solve this problem? Roll number 30, Maniraj. Roll number 30.
Yes, sir.
So how many boundary conditions needed to solve this problem?
Three.
Yeah, roll number 32, Lias.
Yes, sir.
So how many boundary conditions are expected that you will be needing to solve the given problem? Expectation is very, very important. Solving, if you are you are interested in working in modeling of the any subject, take heat transfer, mass transfer, momentum transfer, kinetics, thermodynamics, anyway, expectation is very important. What is your expectation out of a given problem, expected result, then you will try to search for a suitable theory. So expected boundary condition. So given a problem, now problem is discussed. So what will be the expected number of boundary condition needed to solve this problem? Lihas?
Uh, the three boundary conditions.
Why?
So first will be theta.
No,
Theta
why?
finite.
I'm not telling how, which. I'm taking why you needed three boundary condition.
Sir, to get
How you have decided? Why not one? Why not two? Why not 10? Why you are told only three?
sir, to solve R, right,
Yeah.
and one
But
for Z.
because I have second order differential equation with respect to R, to solve this,
Yes.
I need a two boundary condition. I'm expecting first order differential equation with respect to Z. Hence, I need a one boundary condition. So total, I need a three boundary condition. What are the three boundary condition for this problem? So these are the expected boundary condition. Certainly, at R equals to 0, temperature will be finite. Okay. So you cannot have undefined or infinite value of temperature at R equals to 0. At R equals to R, so at this wall, a flux is given, which is constant. Okay. Heat given, rate of heat given per unit area. Heat per unit time per unit area is constant at R equals to R. This is another boundary condition. And third boundary condition is initial temperature of the fluid is given. Z equals to 0, T is T1. Okay, T is T1. So this is okay. This I can use. This I can use and I can solve the problem. Okay, because I am expecting that I will be getting a second order differential equation with respect to R. But first order differential equation Z equals to 0, T equals to T1, whether I will be able to solve this problem. Because this is what expected temperature profile. Expected temperature profile I should get the boundary condition from expected temperature profile. Okay. I should get the boundary condition, or from boundary condition will be satisfied with the expected temperature profile. If I put Z equals to 0, okay, Z equals to 0, what I will get temperature equals to function of R. This cannot be solved actually for this third boundary condition. And certainly I need to involve R also along with this three boundary condition. So instead of using this first boundary condition, what I will be doing, I will be taking a heat balance over a length L. So that this F of R will also get involved along with this boundary condition. So you can say the modified version of same boundary condition I will be using along with this Z and Q0. Z and Q0 along the length. What is the final temperature? That I will be using as a third boundary. Okay, so you can see if I keep Z equals to 0 here, so it is not satisfying F of R. I don't know what is F of R. Here F of R is constant. F of R is constant. So only this boundary condition will not be able to solve the gradient with respect to Z. So what I need to do is I need to take a heat balance over some length L. So combining these two boundary condition and getting this modified third boundary condition, which will be used here. This is clear to everybody. Now, what will be the dimensions of differential shell? Roll number 35, Praneeth.
So like since temperature is varying across two directions, we can take dr, dz and total 360 degrees theta.
Very good. So delta R in R direction because temperature is function of R. Delta Z in Z direction because temperature is function of Z. And theta, it is constant, hence total theta 360 degree. Okay. So this is my pi. So this is the differential temperature delta R. Okay. This is the delta R. This is delta Z. Now calculate the flux. Okay. Flux. So if say QR, QZ and not QR, you take a combined energy flux because this is a flow system. This is the flow system. You can use a combined energy flux. Here you can use enthalpy or internal energy. So you can use enthalpy also because there will be gradient of pressure also. So better you use enthalpy because pressure is accompanying with internal energy to give the enthalpy. In last class itself we have discussed because there is a variation of pressure. So it is better to use the enthalpy. So enthalpy, combined energy flux in enthalpy form that you can use. Flux multiplied by surface area, flux multiplied by surface area coming in, going out, plus total forces acting on a system. So here gravitational force is acting on a system, which will also give rise to heat because of viscosity and all that. Total forces acting on a system and work done by that total forces that will be equals to 0. Okay, and heat added is a kind of a boundary condition that we will be using. Heat added is a boundary condition that we can use actually. Now already we have solved couple of problems. So this will be a surface area. What will be surface area for R direction? It will be twice pi R into delta R. And what will be surface area for Z direction? PR will be the flux perpendicular to flux in R direction or perpendicular to this surface area. Okay, similarly, what will be surface area for Z direction? It will be a roll number 36. Yes.
Yes, sir.
What
It
will be
will be
surface?
2 pi r, sir, cross-sectional area, so 2 pi r into delta r.
2 pi r into delta r. Okay, 2 pi r
Yes,
into delta r. And what will be flux in Z direction? EZ.
sir,
EZ.
EZ.
Combined
Yes, sir.
energy. Okay.
Yes.
So this coming in and going out, this coming in, going out, plus total forces acting on a system actually. And so, and you will be needing a velocity profile also because this is convective flux. It is dominated by convective flux in Z direction. So you will be needing velocity profile also. And already we have solved this problem for momentum transport. And this is the velocity profile which we got actually. Vz equals to delta p r square divided by 4 mu l. So which is equals to Vz max. Vz max 1 minus r by r square. Okay, this is the velocity profile. If this velocity profile is not given, so you need to solve first of all this problem to get the velocity profile. Because here you cannot assume constant velocity profile with r because velocity will change in r. For laminar flow, we will have parabolic velocity profile. So if you assume that constant velocity with respect to r, it will be plug flow. Okay, laminar plug flow. That will not be case. Okay, that will not be case. So this will be the actual velocity profile. And how to get this velocity profile? Roll number 37.
Classes we have got that by cell balancer in cylinder.
Cell balance or momentum transfer first of all.
Yes, sir.
Which momentum balance you will take? Which momentum balance? X, Y, Z or R theta. This is R theta and Z.
So this is for as the velocity in that case. I mean, in the earlier classes we discussed for variation in z direction. V is a function of
Variation
r.
in Z direction. Variation. So this is Z momentum balance, R momentum balance, or theta momentum balance.
So z momentum in r direction.
This here itself it is given Vz. We are discussing Vz. Mass into
Yes.
velocity is momentum. So we are discussing a Z momentum balance equation, and this velocity is varying only in R direction. So shell
Yes.
energy balance equation. So rate of combined energy flux in. For this case, in R direction and in Z direction, rate of combined energy flux going out. In R direction and Z direction, rate of work done on a system by external forces. External forces are the gravitational force in this case. Gravitational force, already we are discussing momentum transfer. So there is no energy consumed, okay, and generated or consumed, that equals to 0. So total energy coming in R direction. Roll number 38.
Yes, sir.
What will be this value?
Sir, total energy, sir, combined energy flux into area ER into 2 pi R delta Z. R direction 2 pi R into delta R.
R direction 2 pi R into delta R.
Sir, delta Z.
Delta Z. And that is estimated at R. Okay.
Yes, sir.
So this will be twice. This is the combined energy flux perpendicular or combined energy flux in R direction. And this is the surface area estimated at R. This is the energy coming in my differential shell in R direction. This is total energy going out from my differential shell in R direction at R plus delta R. So this will be at R plus delta R. Okay, so
Yes,
twice. So approximately this delta R is very small as compared to this R. Because this is R plus delta R. Delta R is very small as compared to R. Hence I can neglect this R and this will be twice by R ER R plus delta R. So roll number 39, Deepam.
Yes, sir.
So what will be this total energy coming in my differential shell in Z direction at Z?
Sorry, sir.
Very good. Here itself given, na? Here ER is there, so instead of ER it will be EZ estimated at ZZ multiplied by perpendicular surface area. That perpendicular surface area is also discussed. And
Sir.
you don't want to take the efforts, you just want to say the sorry, that's all.
No,
So
sir.
this is what EZ multiplied by perpendicular surface area, and this perpendicular surface area is also told to you. This is also told to you. What is this figure is showing actually? This is so clearly showing you actually ER, and this is perpendicular, and still you are interested in sorry only. That is very good actually. Okay, this will be a total energy going out of the differential shell, that will be Ez estimated at Z plus delta Z multiplied by same, and this will be work done on a fluid by the gravity. External forces acting in the system is a gravity. So this will be a, you can say this is work done. Okay, work done. So the force, okay, force per unit area, and that you can just gravitational force multiplied by this, you can say volume, okay, and this will be a velocity and density. So this will be a kind of, you go in a consistency of unit, and this will be a work done by a gravity on a fluid, flowing fluid. This is what work done, because fluid is flowing because of gravity, because of this force. Okay, so gravity or that pressure is there actually. This is already here also pressure variation is involved, and some work is also done. So that will be a rho into Vz into Gz twice pi R delta Z volume. Okay, this will be a work done on a fluid. Okay, by gravity. This is clear to everybody? Okay, now rearrange this equation, and so keep it in this shell balance equation. So what equation you will get? So this is what you will be getting. What kind of rearrangement? Okay, now you need to rearrange this input minus output, this input minus output plus this equals to 0. And then don't change the location of R actually. Don't change the location of R. Just let it be R wherever it is R, because you know that ER is a function of R. ER is a function of R. Here anyway that Z is not coming. Okay. So don't change the location of R. So what kind of roll number 40, Ravi? Roll number 40.
Yes, sir. Yes, sir.
So
Yes,
what
sir.
kind of mathematical arrangement you needed here?
Arrangement, sir.
Yeah.
Sir, usually we used to do a bit, just taking limit delta R is equal to
No.
0.
First of all, this R plus delta minus R divided by delta. First of all, you need to multiply it by -1 and use the definition of differentiation. Okay, multiply
Yes,
it by
sir.
-1 and use the definition of differentiation. So this is what you will get actually. 1 upon R. Okay. So 1 upon R. So this R is there. Okay. Divide by this R. Actually, after getting a differential equation, you can divide it by R. 1 upon R d by dr of R into ER minus dEz by dz plus rho into Vz into G, that equals to 0. Okay. Now you substitute the definition of ER. Already we have discussed. This is combined energy flux, which will have convective energy flux plus conductive energy flux plus work associated with a molecular transport. Okay, this will have 3 components. Combined energy flux will have 3 components. First one will be a convective energy flux, then conductive energy flux, and third will be the work associated with the molecular transport. And this convective energy flux again will have 2 components. One will be a work or this flux because of kinetic energy, and flux because of internal energy. Okay, internal energy flux and kinetic energy flux that will have. Now internal energy can be written in the form of enthalpy also. That also we have discussed. So you use enthalpy term and substitute the definition of ER and EZ, substitute that, rearrange the equation and get this equation. Everybody got the point? Yeah, roll number 41, Mithilesh.
Yes, sir.
Can you just explain what I told to you?
Sir, we have to substitute the, the kinetic energy in terms of enthalpy in the given equation.
Yeah, but ER, what are the three components in ER first of all?
Sir,
This will have three components. What are three components?
sir, flux and
This is combined energy flux only, but energy flux have three components.
sir, convective flux
Very good.
and
Convective flux.
flux
Second
due
is
to flux due to molecular molecular transport.
That is conductive flux, okay, or molecular transport.
Yeah.
And third one will be a
Third one.
work associated with the molecular motion, molecular transport.
Yeah.
So this is what I was telling actually. This will have a three component. This is not a purely convective. So this enthalpy. So enthalpy you write in terms of internal energy, and that this pressure will go here actually. That will be molecular flux because of pressure fluxes. Okay, molecular flux because of pressure fluxes. That is added here. So this you can take it as a convective flux. This is a molecular flux, and this is the conductive flux, not molecular flux. This is the work associated with the molecular transport, and this is conductive flux. Okay, hence ER. If you substitute ER, so certainly there is no velocity in R direction. Okay, this will be VR. ER, so it will be VR. There is no velocity in R direction. So convective flux in R direction will be 0. So this will be a tau Rz into Vz plus QR. Okay, this will be ER, and that tau Rz will be tau Rz I can get from Newton's law of viscosity. Okay, Newton's law of viscosity minus mu dVz by dr into Vz, and this QR I can get it from Fourier law of heat conduction. This is conductive heat transfer minus k dt by dr. This is clear. ER equals to this. Now Vz. Vz, this will be this half rho Vz square half enthalpy Vz square plus tau Zz. Okay, this is tau Zz into Vz plus Qz. Okay, now this already we have estimated. What is H? H will be equals to H plus P minus P0 Vz. Okay, plus rho Cp T into Vz. This is H. This H minus H0 that already we have discussed in last class. H minus H0 will be equals to this plus this, and this rho into H0 will be a rho into H will be equals to rho into H0 into Vz. So H0, what is H0? H0 is the enthalpy, specific enthalpy per unit mass at a standard condition, at a standard condition, say atmospheric temperature and pressure. This is standard pressure. This is standard temperature. These are constant value. You can take it as a reference point. Okay, this will be a enthalpy at reference point. This is the reference pressure, and this is the reference temperature. So P minus P0 V0. If you are interested in derivation of rho into H equals to this, go in a previous class that we have discussed, and plus Qz. This is plus Qz. Okay, this is Qz. So that will be equals to, and this tau Zz, this is tau Zz, 2 mu dVz by dz, because generalized Newton's law of viscosity, here we will be using generalized Newton's law of viscosity, and this is Qz will be equals to minus k dt by dz. Okay, clear? Now substitute this Ez here and substitute this Er here and rearrange the equation, add all the assumption so that you will be getting this equation. Let's see how many of you can get. Roll number 42, Rishikesh.
Sir.
Are you getting
Yes,
what
sir.
is going on in class?
Yes, sir.
Yeah. Can you just explain what you are asked to do?
Yes, sir. Now we found out the value of ER and EZ,
Huh?
and now we have to substitute it in the
Whether
above
you
in the
got this
first equation.
differential equation? Whether you
Yes,
got
sir.
this differential equation?
Yes, sir.
No difficulty. This
No, sir.
definition of ER, you got it?
Yes,
Why this is
yes, sir.
zero? Why this is
Yes, sir.
zero for ER?
Because there is no velocity in our direction.
Very good, very good. Okay, there is no velocity in our direction, and this rho into h equals to this. Already we have
Yes,
discussed
sir.
in previous class.
Yes, sir.
Okay, so everything is clear. Now substitute this
Yes.
and try to rearrange and try to get this equation.
Yes, sir. I'm doing.
Just write in a chat box. Anybody getting this equation? Write in a chat box. Now this is substitution and rearrangement. Okay, what is this? From this equation to this equation is a substitution and rearrangement, nothing more than that. Substitution and rearrangement, you collect all the term consist of K and Vz and mu. This is one Vz, you keep it on LHS. So one term, this you can say rho CPT. This term you keep it on LHS, remaining you all transpond on RHS and collect the term having thermal conductivity, all the term having thermal conductivity, all the term having viscosity, and all the term having velocity. So this is one bracket, this is another bracket, and this is third bracket. So very simple, you substitute this, and this is constant actually, T0 is constant. T0 is constant. Whether velocity is varying in z direction. Roll number 46, Aishwarya.
Yes, sir.
Whether velocity is function of z.
Velocity, sir, will function. Yes, sir.
Velocity is function of z.
No, sir. Vz is a function of r.
High velocity is not function of z.
Due to along the length neglected, sir, and effects.
Not neglected. We have discussed also. Everything is not neglected. We have discussed also why velocity is not function of z. Here roll number 47, Gurupreet.
Yes, sir.
Why velocity is not function of z?
So due to continuity equation.
Continuity equation and constant density system.
Yes.
Okay, both this is not just due to continuity equation. This is continuity equation for constant density system. L dot v
Yes,
equals to 0, where you cannot have variation of z velocity with respect to z. Aishwarya, did you got this?
Yes, sir.
When did we discuss this actually? Whether we discussed this in a class?
Yes, sir.
So when did we discuss this?
Means yesterday's.
Not yesterday. So everything we have not discussed yesterday. We have discussed when we were discussing equation of change. Before discussing equation of change, I told that we will be needing the input from continuity equation
For
also. That time
cylinder.
we discussed continuity equation. Del dot V equals to 0. What is that del dot V equals to 0? If we have only z velocity, dv by dvz by dz equals to 0. Okay. So there is no variation of z velocity with respect to z. That also you need to. Okay. So that all the information you can substitute. You can write in chat box. If anybody is getting this, you can write in chat box. Anybody getting this equation? Are you trying or just sitting? Roll number 48, Hansraj.
Sir. Sir, got it, sir.
Got it?
Yes, sir. Means I have not written it yet, but like here I have arranged this equation and I got the final equation.
So can you just show me? Can
Sir,
you just
I have
switch on your camera?
Sir, I have not written the equation, but like I have arranged the equation here on itself, here on the screen itself.
Oh, here on the screen itself.
Yes, sir.
Can you show me where you are sitting? Hansraj?
Yes, sir. So here is the.
You are using background.
No, sir, that was.
Okay, how many of you are in this thing actually? Campus? Oh, hostel room only. Hostel room,
Yes,
na?
Yes, sir, hostel.
How many of you are in campus? So roll number 88.
Yes, sir.
How many people have arrived in a campus? So it's
70.
start applying.
Sir, I don't have exact number.
Okay. So this rearrange the equation. So this is what I was telling. So this is same equation. Now substituting the definition of ER. So you can see d by dr of this is ER. This is ER minus this is EZ. Okay, ER minus EZ. Okay, this is ER. Okay, this is complete ER and this is complete EZ. Okay. Anybody got any difficulty? This is ER completely. This is ER and this is EZ. This is the definition of ER. This is the definition of EZ. And this is as it is. Now next step. It is done. Okay, this is distributed. This differential is distributed here. This differential is distributed here. This is as it is. This is as it is. Okay, this is just rewritten. Mu Vz into dVz by dr into this thing actually. Now here you can see that d by dz of Vz is 0. This will be 0. d by dz of Vz is 0. So this will be 0. This will be non-zero. 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 All other things are 0. Only this is 0 actually. Okay. So anyway, this is 0 del P by del Z. Okay. Oh, this is actually written in product form actually. This okay, Vz is constant with respect to Z, but P is changing. Okay, that you can take it out actually. So so you can use a product rule and then use d by dz of Vz equals to 0. Otherwise, this is using product rule and remaining thing is same. Okay. Z is considered is constant with respect to Z here. Now rearrange the equation. This is again rearrange the equation. So you can see this is R multiplied by R. This will be 0. And this is scale. And here this R will go here, minus, minus. And just multiply this 1 upon R inside the bracket. And this remains as it is. This remains as it is. This remains as it is. And everything. This 1 upon R is multiplied with all the terms in the equation. Okay. Now you can see this you take LHS on LHS and remaining all viscosity term you arrange, all thermal conductivity term you arrange, and all velocity term you arrange. Okay. So what you do, you take this to LHS and you arrange all the viscosity term like this term, this term, this term, viscosity term, and your thermal conductivity term and velocity term. To rearrange this equation. Okay, this is both CPT. Okay, this is taken to LHS. This is thermal conductivity having two terms. This is viscosity term. This is also viscosity. This is also viscosity. This Vz you can take it as a Vz, common Vz, and rearrange the equation. Okay, so this is what equation you are told to derive. Everybody got this equation? Yeah, anybody is getting this equation? On notebook. Anybody has got this equation on notebook after substitution? Anybody got this equation? Pritesh, are you able to hear me? Did you got this equation?
I'm still doing. I haven't got it yet. I'm writing.
You are writing. So now this equals to 0. This equals to 0. Can anybody in a class tell me why? This whole bracket is equals to 0. Can anybody in a class tell me why? Yeah, roll number next 50. Rashmi.
Yes, sir.
Yeah, this whole bracket. Can you see my cursor?
Yes, sir. Yes, sir.
This equals to 0. Why?
So like when we take convective flux and conductive flux, the conductive flux can be considered negligible.
No. This whole bracket I am talking about. Can you see my cursor? Can you see my cursor?
Yes, sir.
So this Vz bracket minus del P by del Z plus mu whole bracket del V square by del R square plus 1 upon R del Vz by del R plus rho G, that equals to 0. Have you seen this equation somewhere?
Yes, sir. So this is the equation of change.
Very good. This is equation of change for flow through pipe. When we were discussing flow through pipe, that time we got the same equation that equals to 0. This is the Z momentum balance equation. Okay, Z momentum balance equation will give me this equals to 0. Okay. That is why we have arranged this equation in such a that, so all the equations, so this is the same equation, okay, same equation we got actually. Now this is the, so this is Z momentum balance equation. This is Z momentum balance equation. If you, so steady state, this is equals to 0. This is Z momentum balance. Okay, this is Z momentum balance. This is equals to 0 because of steady state. This is 0 because of VR is 0, V theta is 0. This is 0 because velocity is not varying in Z direction. This is non-zero. This is non-zero. Okay. This is 0 because velocity is not changing in theta direction. This is 0 because velocity is not changing in Z direction, and Gz is a gravitational force in Z direction. If you rearrange this equation, Z equation of change, you can see this. Z equation of change is minus del P by del Z. You can see here minus del P by del Z minus del P by del Z plus mu 1 upon R del by del R of R dVr by dr plus rho G Z. Okay, here also Gz, here also Gz. This equals to 0. This is Z equation of change. Okay, this is how you can simplify the equation. Okay, this is 0 because Z equation of change. Now, what more simplification you can do in this equation? So whether you can neglect this, you can neglect this, you can neglect this. Here, roll number 49, Harshavardhan.
Yes, sir.
Yeah. Can we neglect this?
Yes, sir, because the variation in Z direction is not much.
Variation in Z direction is not very much. That is the reason.
Sir, there will be constant heat flux throughout the length, so temperature will remain the same.
Yeah, this delta
Linear.
T by del Z square
The
is neglected.
we had a like a linear profile for temperature versus Z when in the start. So derivatives will be 0.
Just now we are discussing. Roll number 51, Himanshu.
Yes, sir.
Yeah,
Hello.
why delta T by del Z square is neglected? Or can be neglected?
So, same reason I'm not.
Because
The
this
connective,
is
sir,
telling
connective
me
plus conductive flux negligible, sir. Connective plus conductive is dominating over conductive.
very good.
We can say that.
This K into d2T by dz square is an indicator of conductive flux in Z direction. And this term is a convective flux in Z direction. This is the indicative of convective flux in Z direction. K into d2T by dz square is a conductive flux in Z direction. So conductive flux is negligible as compared to convective flux in Z direction. This is in Z direction. Hence can be neglected. Why this can be neglected? Yeah, roll number 53, Shivam.
Hello.
Yeah, Shivam.
So the dou Vz by dou R specifies viscous heating. So
Viscous
we
heating.
can.
Yeah,
Yes,
very
sir.
good, very good. So because we are not looking for a flow of highly viscous fluid. If we are looking for a flow of highly viscous fluid, then this will be also, you need to consider this also. Viscous heating. This is kind of viscous heating, heat generation because of viscous heating. So when say if oil is flowing through water with high density, then because of this, all layers will be rubbing to each other, having high viscous force of attraction that will generate the heat. But that is negligible considering a lesser viscous fluid actually, that can be neglected. Okay, this is equation of change, and this is neglected because heat conduction in Z direction is negligible as compared to convection, and this is neglected because negligible viscous heating. We are not thinking of, we are not considering a problem with a highly viscous fluid flowing through a pipe. Now remaining is this. Now how to solve this actually? That is all. So you can, this is what expected. So you were expecting that convection is dominated in Z direction. So first order differential equation in Z direction. Conduction is dominated in R direction. Hence second order differential equation in R direction. So this is what expected, and this is what you got this equation. Now you need to solve this equation to get the temperature profile. That's all. How to solve this equation, and you can substitute the velocity profile, because velocity is also function of R. Because here we are discussing the variation with respect to R. So you can substitute this velocity profile here, so that this variation of R, velocity variation of R can be considered. So now we can solve this problem. Okay, solving this problem. So how many boundary conditions are needed? So 3 boundary conditions are needed. So 1 boundary condition with respect to Z and 2 boundary condition with respect to R. This is what needed actually, and this we have 3 boundary condition. At R equals to 0, temperature is finite. At R equals to R, flux is given, and at Z equals to 0, temperature is T1. But as I told, this may not be useful because we have a temperature which is a function of R also, and which is not accounted in this boundary condition. So that is what we need to use a condition 4, not boundary condition, condition 4, that we will discuss how. Now you can solve directly also, or you can convert this into dimensionless equation first of all. To simplify this equation, you can convert this equation into dimensionless form. Okay, you can solve as it is using this 3 boundary condition. Only this 3rd boundary condition will not be useful, because this is not catching any of the variation of temperature with respect to R. This is not considering. To consider that, you need to take the heat balance over length L. Okay, that is why you need to consider. You can solve as it is, or you can convert this equation into dimensionless differential equation, dimensionless terms. Okay, for using these dimensionless terms, so what we will be using? Theta, dimensionless temperature. You can see this is the unit of temperature only. Okay, this is the unit of temperature. Dimensionless temperature T minus T1 divided by Q0R. Okay, Q0R divided by K, dimensionless temperature. This is epsilon. Epsilon is a dimensionless radius R by R, and this is zeta. This is the dimensionless length. This is epsilon, and this is zeta. Zeta will be equals to Z, and this is also having a unit of meter only. This is also having a unit of length, you can say unit of length. This is also having a unit of length, meter or centimeter. Rho Cp Vmax R square by K. So for choosing the dimensionless variable, you need to look at the equation carefully, all equation and boundary condition carefully, and select suitable dimensionless variable such that this equation will be simplified. After substituting this dimensionless temperature, dimensionless radius, and this is dimensionless length. This is dimensionless temperature is theta. This is epsilon, dimensionless radius, and this is zeta, dimensionless length. Okay, if theta equals to T minus T1 divided by Q into R divided by K, d theta, what will be d theta equals to? D theta will be equals to dt divided by this. Actually, T1 is constant. Okay, hence dt will be equals to d theta QR multiplied by R divided by K. This is epsilon equals to R by R. Hence, R will be equals to, so this is R will be equals to R into epsilon. D epsilon will be equals to dr by R, or dr will be equals to R into epsilon. This is zeta. Zeta will be equals to Z divided by rho Cp V Z max R square by K. This is d zeta. Okay, d zeta will be dz, and this is constant. This is constant, and dz will be equals to this multiplied by d zeta. This multiplied by d zeta. So substituting this, substitute this for dt here, substitute this for dt here, substitute this for dr here, substitute for this for dz here, substitute this R by R equals to epsilon, substitute this temperature T equals to this actually temperature in terms of this thing, equilibrium. T minus T1. So you can calculate what is T equals to and what is Z equals to, wherever Z is there. Rearrange the equation. So what equation you will be getting? So this is what rearrangement is there. This is R by R. Okay, R by R will be equals to epsilon, and this is T. Okay, this is temperature. Okay, temperature, and this is d zeta. Okay, dt. This is dt equals to, this is dt equals to, and this is d zeta equals to K. This is 1 upon R. 1 upon R. And this is d by dr. This is dr, and this is R. This is dt by dr. Now rearrange this equation. Rearrange this equation, take out all the constant. So what equation you will get? Rearrange this equation. This is making this equation dimensionless. Why we are doing this? Just to eliminate the complexity which we are expecting will get while solving the mathematics of the equation. So we want to simplify the equation so that it will be easier to handle mathematically. Okay, mathematical handling will be easier. That is why this equation, whole equation, is converted into dimensionless form using all these equation, nature of the equation, boundary condition, nature of the boundary condition, observing this, so we can convert that into dimensionless equation. Now after rearranging this equation, you should be able to get this equation. So 1 upon epsilon square d theta by d zeta, that will be equals to 1 upon epsilon d epsilon into epsilon by d theta by d epsilon. Anybody getting this equation?
Can you once again repeat, please?
Yes, Shivan, did you got this? Yeah, Pritesh.
Yes, sir. So can you once repeat?
Getting, yeah, you. Anybody else is getting this equation? So you can write in a chat box. Anybody got any problem, difficulty in rearrangement of this equation, assumption, anything? Now we need to convert the boundary conditions also. This is what equation I have. Okay, this is what equation I have, and how this boundary condition will change at r equals to 0. Instead of at r equals to 0, what I will tell? I will say at epsilon equals to 0, theta is finite. Okay, this will be boundary condition. Ritesh, tell me.
Sir, can you please repeat that previous question?
Your voice is breaking, Pritesh. You can write in chat box. Who wrote not getting? Somebody wrote not getting. Yeah, Pritesh, you are not getting the equation or what? What you are not getting? You are not getting this equation? Your voice is breaking, Pritesh. You can write in a chat box. Repeat once. What you need to repeat? This assumption is okay? Did you got this equation? You can write in chat box. Yes, you got this equation. This assumption is okay. Whatever assumptions you have, this is equation of change. This is conduction is neglected in z direction, and this is viscous heating is neglected. This is okay, and this is the velocity profile. Substituting this, this is the equation we got. This is okay. Yeah. So now these are the three boundary conditions. Now you can solve as it is. You can solve as it is, but to simplify, we are converting this into dimensionless equation. So for that, we'll be using dimensionless temperature, dimensionless radius, and dimensionless length. So dimensionless temperature is theta, dimensionless radius is epsilon, and dimensionless length is zeta. And what should be this dimensionless value? For normalizing, what value should be used? That you need to decide based on, after observing this equation carefully and boundary condition carefully. Okay, you need to observe this equation and boundary condition carefully, such that after converting this equation into dimensionless form, you should be able to get a simplified equation. So this is the dimensionless temperature I am using. You can see this is the normalizing temperature actually. This is temperature, this is the unit of this is temperature. You go in, this is the flux radius and thermal conductivity. This is again dimension radius, capital R is a normalizing radius. And this is again a length of meter, rho Cp, this is specific heat at constant pressure. Okay, heat capacity at constant pressure actually, specific per unit mass. Density Vz max R square divided by K, it will have unit of meter. So this will be dimensionless zeta, dimensionless length, dimensionless radius, and dimensionless theta. Is it okay? Okay. Now substitute this everything. This is dimensionless temperature. So d theta will be equals to dt divided by this constant. You can get dt value. Similarly, this is epsilon. So you can get r. You can get d epsilon and dr. Similarly, this is zeta. You can get d zeta and dz. This is what you get actually. This you got this. Now substitute everything. So here this is okay as it is. Okay, this is as it is. So you can see this equation. So this is as it is. 1 minus r. R is r into epsilon divided by r. dt. What is dt equals to? dt equals to d theta q r divided by k. This is dt. And it is dz. You can see this is dz. And this is k. 1 upon r. 1 upon r. d by dr. This is dr. And this is r. And this is dt. Again, this is dt. And this is dr. Now rearrange the equation. Take out all the constants. Q0 is constant, R is constant, K is constant. Take out all the constant out and rearrange the equation. Rearrange this equation. Take out this R constant. This will, you can say this will cut with this actually. This R square will cut with this everything, and you will get this 1 upon epsilon square d theta by d zeta. That will be equals to this K will get cancelled. Okay, with this K. D epsilon 1 upon epsilon is this, 1 upon d epsilon is this, into epsilon d theta by d epsilon. This is what you should get. Are you getting this? Yeah, Pritesh.
Sir, I understood. Just canceling better.
Okay, now as we have changed the equation, now you can see this equation looks simpler, na? This equation looks simpler as compared to this equation. That is what our main intention was there. That is how we need to select these dimensionless properties, such that this mathematical complexity will be reduced. Mathematical complexity will be reduced, but on the same hand, we need to change the boundary conditions also accordingly. So we need to change the boundary conditions also in terms of theta, zeta, and epsilon. Okay, theta, zeta, and epsilon. So these are the boundary condition. At epsilon equals to 0, theta is finite. At epsilon equals to 1, okay, epsilon equals to 1, you can say k dt by dr. You substitute this dt by dr and you rearrange this equation. So you will get d theta by d epsilon equals to 1. And at z equals to 0, zeta equals to 0, theta equals to 0. Substitute this t1, okay, t here, and you will get theta equals to 0. So these are the boundary condition. Now this problem is changed. This was our original problem. Using this dimensionless temperature, dimensionless radius, and dimensionless zeta. So we got this equation. Now this equation can be solved very easily actually. This is very easy equation to solve actually. Only the thing is now as we got temperature profile that for T, similarly we need to assume the temperature profile with respect to theta. This is T is a function of R and Z. Similarly, zeta is a function of epsilon and zeta. Theta is a function of epsilon and theta, that will be equal to C0 zeta. So converting this into epsilon and zeta, psi, this is psi of epsilon. This is f of r, function of r, this is psi of epsilon. So this is the expected solution for this problem. This is expected solution for this problem. So you can see at epsilon equals to 0, theta is finite. I may get this boundary condition from this based on a value of this psi epsilon. At epsilon equals to 0, theta is finite. That depends upon a function psi. Similarly, at epsilon equals to 1, epsilon 1 equals to d theta by d epsilon equals to 1. Again, that depends upon this function. I may get this equation. But for zeta equals to 0, if I substitute zeta equals to 0, I need theta equals to 0. So it means that psi of epsilon equals to 0. That is not possible. Psi of epsilon cannot be 0. Hence, this boundary condition is not enough to solve the relation between this solution and this differential equation. Instead of this boundary condition, I need to use the energy balance. I need to use some what is happening over a length L. That information is needed so that it will be accounted for this epsilon, this psi of epsilon. Okay, if what is happening over the length L, that is very, very important, because just this boundary condition at zeta equals to 0, theta equals to 0, it is giving me psi of epsilon equals to 0, which is not true. Hence, I need to add the information in this boundary condition number 3, what is happening over, say, length L. I can take any length L and exactly what is happening over length L. That information will be related to this psi of epsilon, function of R. T is a function of R. So this boundary condition can be satisfied for this differential equation as well as solution. This is also can be satisfied. That all depends upon psi of epsilon. But this is not true. This is not satisfying. I cannot satisfy this solution using this boundary condition. So certainly I need to change this boundary condition, or I need to add the information in this boundary condition number 3. What is happening over a length L. So instead of that, we'll be using a condition. Okay, below equation is not satisfying boundary condition number 3. So I need to add a little more information in this boundary condition number 3. For that, what I am doing is, instead of this just using the information at this temperature, so I will be selecting some length L, okay, some length L, and taking the energy balance, and instead of using just purely this boundary condition, I will be using this energy balance as a condition number 4. So what exactly? So energy balance. So energy is coming in here. So energy is added here and energy is leaving here. So if I know the energy coming in here T1, and this is also boundary condition, using boundary condition I can use this, and you can have this boundary condition energy out here. So if you total only in Z direction, if I calculate and substitute everything here, so what I can do is, so this is the reference here actually. So this will be energy going out. Okay. So 0 to 2 pi, 0 to R, rho Cp T minus T1 Vz R into dr. You substitute this Ez. So this is Z direction only. This is Ez moving in Z direction. Substituting everything here and integrating over 0 to R. Integrating over 0 to R. So I'll be getting this. And what will be the energy content here? So energy content, this energy content here minus here. That will be this actually, rho Cp T1 minus T0. So this will be the energy added. So this T rho Cp T Vz R into dr 0 to R will be the energy coming in. Rho Cp T1 Vz R into dr is the energy going out. In minus out is the energy added here. So instead of using just T1 temperature here, so I'll be using this. This is actually modified. This is modified where you can see temperature a function of R. That information is accounted along with boundary condition number 3. That is main intention, so that we can use that condition for solving our differential equation. This is clear to everybody? Okay. Now this equation also can be, this is condition number 4, which can be used. This is nothing but the boundary condition number 3 only. You can see at Z equals to 0, temperature is T1. At Z equals to 0, temperature is T1. At Z equals to Z1, temperature is T. Any temperature T. Any temperature T. And this is twice pi R into Z. What is the total Z here? Length. What is the energy added? That will give me this information. So this is nothing but modified boundary condition number 3. Now this can be converted into again dimensionless form. Okay, using this dimensionless temperature, dimensionless radius, dimensionless length. So what is this boundary condition? Zeta. Zeta will be equals to 0 to 1. Theta is varying from this R. Epsilon is varying from 0 to 1. Theta, which is a function of epsilon and R. Theta, which is a function of epsilon and R. 1 minus epsilon square epsilon d epsilon. So this is what you will get actually. This is theta, which is function of epsilon and R. 1 minus epsilon square epsilon. You substitute all these dimensionless number. Now, instead of this, I will be using this condition number 4. Condition number 4 to solve this. So now this boundary condition number 1, boundary condition number 2, and modified boundary condition number 3, which is condition number 4. Using this, I need to set up this whole problem and try to prove that this is my solution for this differential equation, which is satisfying all these 3 boundary conditions and getting the value of C0 and all the constant in this psi of epsilon. Yeah, roll number 88. Pritesh?
Yes, sir.
You got this?
Yes, sir.
Okay. Now solution, how to solve is very easy actually. Using this solution, how this solution is assumed actually or expected. So this is also to simplify this so that one dimensions will be eliminated. One dimension will be eliminated. So this is my expected solution. This is my differential equation. So I'll be getting the value of d theta by d zeta. What will be d theta by d zeta? D theta by d zeta will be a C0. Okay. and d theta by d epsilon. D theta by d epsilon will be a d psi by d epsilon. Substituting in this equation, what is d theta by d psi? D zeta, that is equals to C0, and d theta by d epsilon is a d psi by d epsilon. Substituting this equation, this differentiation, this dimensional differentiation is eliminated. So this you can see 1 upon epsilon square C0, that equals to 1 upon epsilon d by d epsilon psi d psi by d epsilon. Now this is the two-dimensional, one parameter, single parameter, two-dimensional equation. This is the one parameter, one-dimensional equation. That one dimension is eliminated, zeta is eliminated, z is eliminated actually. That is why this kind of solution is assumed. So while assuming this solution, you need to think of what is a differential equation you have, what is the problem you have. It should co-op with both your mathematical problem also, your physical problem also. It should co-op. It should ease your mathematics involved in solving the problem actually. That is what main intention is there. So that is d epsilon. Again, now this solving this is very easy. Integrating this equation twice. Now this rearranging this equation and integrate this equation twice. So first of all, you can move this epsilon here. So this is epsilon. This epsilon is moved here. Now integrating this equation. Okay, this is integrating, first integration. Integrating this equation, this will be epsilon square by 2 and this will be epsilon raised to 4 by 4 plus C1, one more constant of integration. Again, rearranging the equation. So rearranging with respect to this epsilon. So this will be a epsilon by 2 and C1 by epsilon. Again, integrating the equation, epsilon of psi, that is equals to C0 epsilon square divided by 4 minus epsilon raised to 4 divided by 16 plus C1 ln R plus C2. Okay, this is what epsilon of psi. And what is my theta? Theta is C0Z plus epsilon of psi. So what will be theta? This is my temperature profile. So this temperature profile, theta, will be equal to C0 zeta plus C0 epsilon square by 4 minus epsilon raised to 4 by 16 plus C1 ln epsilon plus C2. Now how many constant we have? 1, 2, 3. 3 constant and 3 boundary condition. So we can solve the problem very easily. So these are the 3 boundary conditions. So you can see using this boundary condition, what will be the outcome? Epsilon equals to 0, theta is finite. What it will give me? Here roll number 54, Dikshika. Roll number 54, Dipshika.
Yes, sir.
So using boundary condition number 1, can you estimate any one of the constant from C1, C2 and C0?
Yes, sir, I'm doing.
You need not to do anything. You observe the equation. You are not writing anything. What you need to do? To substitute this boundary condition. So how you will do?
Yes.
So this is almost 10 times we are using this logical boundary condition.
Yes, sir.
So what will be the outcome? Whether I will get C0, whether I will get C1 or whether I will get C2. what I will get?
Sir, epsilon equals to 0, theta will be 0.
Yeah, roll number 56, Jitendra.
Yes, sir.
Tell me.
Hello, sir. Am I
Yeah, tell
audible?
me how to use. Yeah, you are very clear, audible.
Sir, C1 will be 0
Why?
because J is 0, so phi should be finite.
Yeah. So this epsilon or xi, whatever you can call psi,
C1
if you
ln
keep psi equals to 0 here, so ln 0 is undefined. Okay,
Yes,
ln
sir.
0 is
So C1
undefined.
should be 0.
So C1 should be 0 or C1 should not be there. Okay. So substituting. So Deepshika, can't you understand this? This is first time you are using this boundary condition.
Then I got that C1 will be 0.
But how? Then why you are keeping quiet?
Hello?
Then why you was keeping quiet? Okay. So using this first boundary condition, so I will call it as a psi. So this is psi for me. This is zeta for me. This is epsilon. This is epsilon for me. This is zeta for me. This is theta, and psi is that psi of epsilon. Okay. So this, if you substitute this 0 here, ln 0 is undefined. So C1 must be equals to 0. Okay, C1 must be equals to 0 because ln 0 is undefined. So I cannot have undefined value of theta at any corner of my this thing. Okay. Now this C1 equals to 0. This is simplified. Now only two constant and two boundary condition. Now second boundary condition. Epsilon equals to 1. D theta by d psi equals to 1. So d theta by d psi, first of all, d theta by d psi. This is d theta by d psi. And put epsilon equals to 1 here. D theta by d psi. Differentiate this equation with respect to psi. So this is psi for me. This is psi. D theta by d psi equals to C0. So anyway, this is constant with respect to psi. There is no psi in this. So C0, integration of this, actually. Integration of this, epsilon by 2, and this is integration of this. Anyway, this is constant. Not integration, differentiation. Differentiation of this, and this constant of differentiation is this, actually. This equals to 1 at zeta equals to 1. So this equals to 1 at zeta equals to 1. That will give me, okay, this equals to 1 at psi equals to 1, not zeta. Psi equals to 1. So rearranging this equation, what I will get? C0 equals to 4. Here, rule number 58, Devang Joshi.
Yes, sir.
Did you got this C0 equals to 4?
Yes, sir.
Any confusion in C1 equals to 0?
No, sir.
Okay. Now substitute this C1, C0 and C1. So what the equation C0 and C1 in this equation, what I will get? This is the final equation. This is the final temperature profile equation, 4 zeta plus epsilon square minus epsilon raised to 4 divided by 4 plus C2. Only one constant remains, and this is the boundary condition. Now integrate this. Integrate zeta will be equals to integration of this theta from 0 to 1 multiplied by 1 minus epsilon square. This is condition number 4. That energy balance I already explained to you. So instead of using boundary condition, we'll be using this condition number 4, boundary condition number 3. Only boundary condition number 3 is not sufficient to discuss the variation of theta with respect to zeta. Hence, this one condition number 4 is used actually. So now integrating this, first of all, multiply this by 1 minus epsilon square epsilon d epsilon, integrate it over 0 to 1. Okay, this is, you can say theta, this is theta 1 minus epsilon square epsilon d epsilon. So now integrate between 0 to 1, and that should be equal to zeta. That will give you a value C2. Okay, now integrating d epsilon varies from 0 to 1. Now integrate this equation. So what is done actually? First of all, this epsilon and this bracket is multiplied. So here I will get epsilon minus epsilon cube. This is as it is. This is as it is. Okay, so all non-epsilon term are collected actually here. This is 4 zeta plus C2, and this is epsilon square and minus epsilon raised to 4 as it is. This epsilon is multiplied, and then you can multiply this bracket and this bracket. First of all, multiply this bracket by this bracket. So multiply this bracket by this bracket. This is what you will get. Multiply this bracket by this bracket. Okay, this is what you will get. If you multiply epsilon by this, epsilon cube, multiply this by epsilon, this will be epsilon 5, this will be epsilon 5 raised to 4, and this will be epsilon raised to 7 raised to 4. Okay, now this bracket and this bracket can be also multiplied actually. So rearranging, now integrating the equation. This is integrating for epsilon 0 to 1. Epsilon 0 to 1. This is integrating this equation. Integration of this will be a epsilon will be epsilon square by 4. This will be epsilon raised to 4 by 4. This will be epsilon raised to 4 by 4. This will be epsilon raised to 6 by 6. This will be epsilon raised to 5, 6. This will be epsilon raised to 6 by 6 into 4, 24. This will be epsilon raised to 8 by 8 into 4 is 32. And put epsilon 0 and 1. Integrate between 0 and 1. So this is what 0 anyway, that will be 0 minus 0. Okay, everywhere you will get 0. This will be just substituting 1 minus 0 and rearranging this equation. Again rearranging this equation. Okay, rearranging this equation. So what will be C2? C2 will be equals to 7 by 24 minus 7 by 24. Rearranging mathematically equation and getting the value of C2. C2 is minus 7 by 24. So substituting the C2 in the equation, what I will get? Theta. This is my temperature profile. Theta, which is a function of epsilon and zeta, that will be equals to 4 zeta minus epsilon square minus 1 upon 4 epsilon raised to 4 minus 7 by 24. This is my temperature profile. Okay, this is my temperature profile. So now this is actually in dimensionless temperature form. So you can write in actual temperature form. This is what dimensional temperature we have used. This is what dimensionless radius we have used. This is what dimensionless zeta we have used. So we can get this. This is my temperature profile. So T minus T1 divided by Q0 R into K, that will be equals to 4K. This is 4Z divided by rho into Cp into Vz max R square divided by K plus R by R square minus 1 upon R. Now you can see this is a linear variation with respect to Z. Okay, this is linear variation with respect to Z, and this is indicating a function of R. So this temperature is a linear variation with respect to Z and a temperature of function of R. So this is exactly what we have expected, and we got the temperature profile. So anybody has any confusion over this temperature profile? Okay, then surface temperature. What will be the surface temperature? Surface temperature also keep on increasing. What will be the surface temperature? Keep R equals to capital R. That will give me a surface temperature. So what will be surface temperature? T0 minus T1 divided by Q0 R. That will be equals to 4 and plus 1. 1 square is 1 minus 1 upon 4 minus 7 by 24. That will be equals to 4 zeta plus 1, and that will be equals to 4 zeta. This will be equals to 4 zeta. This is zeta actually. 4 zeta plus 11 by 24. This will be my surface temperature. You can see it will linearly increase with zeta. It will linearly increase with Z actually. Okay, this T0 is a surface temperature which will be linearly increasing with the zeta with some other constant. Okay, so this is linear variation. Then this is, you can calculate this T0. Rearranging this equation, T0 will be equals to T1 plus linearly varying with zeta plus 11 by 24 Q0 R by K. This will be my surface temperature. Surface temperature increases with the Z with this value. As move down the line Z direction, zeta will increase. Zeta will increase. The T0 will also increase. Larger the length of the pipe, larger will be the surface temperature at the end of the pipe. Smaller the length of the pipe, smaller will be the surface temperature at the end of the pipe. Okay, that this is the surface temperature. Now average temperature. This is clear to you. Surface temperature will be T0. This is average temperature. How to get the average temperature? It will be integrated over 0 to R. Integrated over 0 to R because it is a function of R. Average surface temperature over a cross section. This is not over a Z. This is over a cross section. Okay, over a cross section and over a. This is over a given cross section. This is not average temperature from starting point to end point. This is at any cross section. At given cross section, given value of Z, what will be the average surface temperature? This will be integrated over 0 to R divided by 0 to R, or integrate it over surface area. Anyway, it is constant with respect to theta. So that will give me T1 plus. So you just estimate similar to this. Similar to this, you substitute this temperature profile, integrate and get the average temperature. That will be equals to T1 plus 4 zeta plus 7 by 24 Q0 R by K. Exactly similar manner, get this value of average temperature in a manner which we got a surface temperature. This is the average temperature over a given cross-sectional area. Okay. So now this is the bulk temperature. What will be the definition of bulk temperature for flow through pipe? What is the definition of bulk temperature for flow through pipe? Roll number 59, Nikita. What is the definition of bulk temperature? Definition for flow through pipe.
So when we're talking about bulk, it will relate to the velocity. So into velocity and divided by average bulk velocity, I guess.
So velocity average temperature, that is called as the velocity average, because average velocity is a general characteristic velocity taken when we are discussing flow through pipe. Characteristic velocity is taken as an average velocity. So bulk temperature will be a velocity average of a temperature. This is what is this? This is the velocity average of the temperature. Because average velocity is taken as a characteristic velocity for flow through pipe. So now you can this Vz integrate it over 0 to R, 0 to 2 pi, and this will be bulk temperature. So bulk temperature will be a T1 plus 4 zeta Q0 R by K. You substitute this T here and get this exactly in similar manner which we got in this. So now rearranging this equation. Okay, this is my surface temperature. This is my surface temperature. This is my bulk temperature. So what is the definition of Nusselt number for this actually? Nusselt number. What will be the Nusselt number for this? Okay, anyway, so rearranging this equation, T minus T0. What is T minus T0 minus TB? This is the surface temperature minus bulk temperature. So this is the surface temperature we calculate. This is the bulk temperature we calculate. That will be equals to 11 by 24 Q0 R by K. Okay, rearranging this equation. So this is QD. Instead of radius, diameter is used, 11 by 24. Rearranging this equation, so this will be a Q0 D by K T0 minus bulk temperature, that is equals to 48 by 11. If you observe this, what? If you observe Q0 divided by T0 minus bulk temperature, this is equals to heat transfer coefficient. Heat transfer coefficient for heat flowing from pipe surface to inside the fluid actually. Q0 is the flux, and this is T0 minus TB, and this will be H into T0 minus TB, that will be equals to Q0. Hence, Q0 divided by T0 minus TB will be equals to H. HD by K is the Nusselt number. So Nusselt number will be equals to 48 by 11. So Nusselt number for this case, it is observed to be a 48 by 11. This is very specific and very important observation or finding for this problem when you have a flow of fluid through a pipe and which is constantly heated or uniformly heated with a flux Q0 on the wall. So overall, for this problem, Nusselt number is observed to be that is equals to 48 by 11. Okay, so this is what we are expected to discuss this actually.